Welcome Mechanics of Materials students. In this lecture we're going to be discussing strain transformations. So hopefully all of you have gone through sections on stress transformations in which you are looking at the state of stress at some angle, reference to some reference angle, usually whatever is denoted as the x-axis on your part, and looked at how that change in orientation changed the state of stress. So you went from, in plane stress for instance, you went from an xy coordinate system to an x prime, y prime, tilted at some angle theta to the x-axis, and then you developed relationships geometrically to relate the normal and shear stresses in your reference xy coordinate system to your new rotated x prime y prime coordinate system. We can make those same kind of geometric relationships between, or find those between a reference coordinate system and rotated coordinate system for strain. And so we're going to do that, and we're going to find that it ends up looking an awful lot like the rotated coordinate system for stress state, and in fact there will even be a Mohr circle relationship that we can utilize. So we're just going to step through some steps here and start deriving first the strain transformation relationship the way we did with stress, and then we use an example to go over how the Mohr circle applies once we set it up. So we're going to start with just simply a rotated coordinate system. So we have a reference coordinate system x, y vertically and x on the horizontal going to the right. We have some point of interest P out here, and we can draw a radius vector from the origin to P. And we might be interested in the state of strain at P with reference to some coordinate system x prime, y prime that's rotated counterclockwise by some angle theta with respect to the x and y. So both x prime and y prime rotate an angle theta from x or y. So we start with some geometry and we go both ways. First we say, well, let's write an expression for the x coordinate of point P, so that's how far over we go here on the x-axis, so that's x sub P, in terms of what that same x coordinate reference and y coordinate reference would be in our rotated system. So we can say, just using the geometry of the system in a lot of right triangles, we can say that our distance xp, if we wrote it in terms of x prime p and y prime p, and y prime p is over here, we would find that xp is equal to x prime p cosine theta, so that's cosine of our rotation angle, minus y prime p sine theta. And likewise our yp in our reference coordinate system is x prime p sine theta plus y prime p cosine theta. So we have kind of an inverse trig relationship. And we can go the other way, do the same thing, and we kind of get the inverse again. So x prime p written in terms of, so our distance in the x direction of our rotated coordinate system in terms of our xy coordinate in a reference coordinate system will be x sub p cosine theta plus y sub p sine theta, and our distance in the y direction in a rotated coordinate system is negative x sub p sine theta plus y sub p cosine theta. Now these two sets of relationships are going to come in super handy when we start doing differentials of displacement and then relating that to strain. So we're going to just kind of keep an eye on those, and we may have to flip back to them as we move on. We'll just scan out a little so we can see things at the same time. Okay, so we've established the geometry of the coordinates of a given point with respect to our reference coordinate system and a rotated. Now we're going to think back to the relationship between displacement and strain. So we could express the displacement of any point in either the xy system or the x prime y prime system as our standard displacement function expressions u and v. So you're going to take a point in in our xy system, and it will move over in the x direction according to some function u, which is a function of, could be a function of x or y or both. And v is the amount of displacement in the y direction, reference coordinate system again, based on its initial position versus x and y, whatever that was. Same thing with u prime, v prime. So u prime will take a point, and based on wherever it started, with reference to x prime and y prime, it'll move it in the direction of y prime. So it'll move it along in the y prime direction some amount based on wherever it was when it started. And the same thing with v prime. V prime will take a point and it'll move it some distance out in or closer in the y prime direction depending on where it was. So that's, again, a little review of the definition of displacement. Okay. So again, remembering we can express the coordinates or the location of point P in a radius vector if we need to, and that radius vector would end up having x and y or x prime, y prime coordinates like so. So, you know, there's two different ways to express. So now look at strain. So we're going to look at strain in the xx or strain in the x prime x, or strain prime xx. So that's basically, you know, strain in this direction as opposed to that direction. Okay. So strain in the xx direction, we've already established that relationship with displacement. It's strain in the xx, normal strain in the x direction is the partial derivative of the displacement function u with respect to x. So we can write an analogous expression for strain xx in the rotated coordinate system as our u prime first partial with x prime, which we can then kind of take apart and write as a differential function. And that sets us up to think in terms of like a differential operator, which we're going to kind of deploy in the next line. So we could write the partial derivative of our displacement function in the x prime direction with respect to x prime as the differential with respect to x prime, kind of an operator that happens to be operating on whatever this displacement function that carries something some distance in the x prime direction depending on where it was, which is u prime. Okay, now we haul out the chain rule. So we're going to express strain in our new coordinate system, which is what we're really kind of getting at, in terms of x and x prime. So we're going to start with our partial of u prime with respect to x prime, and we're just going to deploy the chain rule, and remembering that u prime is going to have a dependence on both the x and the y coordinate of whatever position we have. So the partial with respect to x prime will have to draw from both the dependence of that displacement with respect to x and with respect to y. So there's basically two components of it. So we have this term showing the x dependence, and then, you know, multiplying by our partial of x with respect to x prime, chain rule, which would just give us our partial of u prime with respect to x prime. And then we have our second part of the chain rule showing that y dependence, and again multiplying by this term to get us back to just everything in terms of x prime. And if we use our operator expressions and say, well, we're going to leave our change in x with respect to x prime and change in y with respect to x prime alone, because those are just geometrical relationships, and leave these partials with respect to our x and y, our original coordinate system, as operators, we can take our u prime out of this expression and just say this whole expression, I'll put it in square brackets, this whole expression is going to operate on u prime. So we're going to have a geometric term for the change in x with respect to x prime and the change in y with respect to x prime. Then we're going to have differential operators with the reference coordinate system, something we know, that are going to operate on this displacement in the new coordinate system. So we can use geometry to relate the change in x with respect to x prime, ends up being cosine theta, our rotation angle, and then the change in y with respect to x prime ends up being sine theta. So those we could just write cosine theta, sine theta, dependent on a rotation angle, we're good. And then we can use the relationship u prime as a function of u and v, drawing back from our fundamental relationships with our geometry and the definition of u prime and u. So I took a brief pause to erase some of the red highlights to make these next points clear. So we left off with application of the chain rule to express the first partial of our displacement in the x prime direction u prime with respect to x prime, and we isolated our partial of u prime with respect to x and partial of u prime with respect to y, the original reference coordinate system, and then our basically change in our reference coordinate with respect to our rotated coordinate system for x and y with respect to x prime. We established back with our geometry that our partial of x with respect to x prime is cosine theta, and our partial of y with respect to x prime is sine theta. And again, this rolled right out of the geometry, and we could look up here and express that. And we came to relating our displacement function u prime with respect to our reference displacement functions u and v. That can be thought of as basically rolling right out of the displacement version of this term. Our relationship of our x prime coordinate to our x and our y, and that cosine and sine theta relationship. So basically every one of these relationships on this line flows from these two geometric relationships up here. So that continues throughout. So if we basically insert the sine and cosine expressions here and here, and then we take the partial derivatives of u prime with respect to y and x in this expression, paying attention to what we're going to learn later, or what we already know about the partial of our displacements with respect to x and y, or x prime and y prime, we're going to end up getting strains. So if we start with the partial of u prime with respect to x, we're going to come down here and we're going to say, okay, fine, I'll take the partial of u with respect to x. Cosine theta is not dependent on x or y, so it stays as a constant. Then I'm going to add the partial of v with respect to x, and again be multiplying by sine theta, which when I multiply by my cosine theta term here will give me a u, or partial of u with respect to x, times cosine squared theta plus partial of v with respect to x times sine theta. So that will give us this term and half of this middle term. Then we'll take in our second term in our chain rule, we'll end up taking the partial of u prime with respect to y, so we'll come back here and we'll end up with the partial of u with respect to y times cosine theta. And then we'll take the partial of v with respect to x times sine theta. All of that will be multiplied by sine theta from our geometric term. We'll end up with the second half of this middle term, and we'll end up with our sine squared term. So again, we've used geometry and we've used the chain rule and put together some derivatives so far. So this line is important because the partial of u prime with respect to x prime is our normal strain in the x direction in the rotated coordinate system. So this is our rotated normal strain. So we have a cosine squared theta, that's our rotation angle, times partial of u with respect to x, which is our normal strain in the non-rotated x direction. We have partial of v with respect to x plus partial of u with respect to y, the mixed partial derivatives. That gives us our shear strain. And I've written this in terms of our tensor shear. We could write it in terms of engineering shear. It's easier to write it in terms of 2 times the tensor shear. And then of course we have our normal stress in the y direction in our non-rotated, our reference coordinate system, times sine squared theta. So a lot of geometry, chain rule, some partial derivatives, and grouping terms. So now we're going to collect terms and use our double angle formula, very similar to what we did when we derived the stress transformation relationship. So we're going to collect our cosine squared theta, sine squared theta, and apply a double angle formula, and then we're going to use our 2 cosine sine and use a double angle formula and collect some terms, and we're going to be able to express our normal strain in the x direction in a rotated coordinate system, so our exx prime, as 1/2 of the sum of our normal strains in the x and y direction in our reference coordinate system, plus the difference in our normal strains in the reference coordinate system divided by 2 times cosine of 2 theta, plus our tensor shear. So that's basically 1/2 of this, times sine of 2 times the rotation angle. So we're back to our 2 thetas. So from theta to 2 theta. So this is setting up to be very similar to our stress transformation relationship and setting up for a Mohr circle. So we can basically do the same thing and isolate an expression for tensor shear strain in terms of all of our in the rotated coordinate system, in terms of our normal and our shear strains and our rotation angle with a reference coordinate system. And this is what we get. We've corrected here. It's definitely it's analogous to tau, but it's not tau. It's our tensor shear. So if you take a look at these and this expression here and this one, and you compare that to our stress transformations, you'll notice that if you use both of these, you can plot a Mohr circle just like you did for stress, where we have normal strain instead of normal stress on the y and shear strain on the x, on the horizontal component axis, and shear strain as opposed to shear stress. And again, we're using tensor shear, so this would be gamma over 2. So we're plotting shear strain versus normal strain, where we plotted shear stress versus normal stress with the stress Mohr circle. So just like in the stress Mohr circle, we have a circle center, which is 1/2 of the sum of the 2 orthogonal reference system normal strains. And then we're going to have an analogous relationship for the radius of the circle, which will give our max shear strain, tensor shear strain. So we'll just take a look at the shape of the Mohr circle again. So if you imagine some theta angle here with respect to whatever the original part was, this is one of our principal normal directions. So we'll have principal normal strains, greatest in the tensile direction. So we'll have the max stress at whatever orientation this point corresponds to, and the minimum stretch or compression if it's on the other side of the axis. And then at the angle corresponding to these 2 points, we would have our maximum shear deformation, so our maximum change in a right angle. So what angles are those with respect to something on the part, the original part that I cared about? Because on the Mohr circle, we're not necessarily sure where those principal and max shear directions are with respect to maybe the direction of loading. So we can look at, say, this point X, which say that corresponded to the X direction in our original part. We could measure this angle here on the Mohr circle if we knew what this coordinate X was, where this was, and we would know how far counterclockwise, so 2 theta on the Mohr circle equals theta on the part. We would know that basically we'll call this theta, 2 theta. So we'd know that theta counterclockwise from our X direction on the part, we would expect to see the most stretch in our actual part. Any particular direction of interest we could call X prime, and so we'll call this angle phi or whatever. I'll just put a little tick mark. So the on the real part, our X prime axis is rotated at half of whatever this Mohr circle angle is. So our Y direction on the real part is up here, and so we have 180 degrees on the Mohr circle corresponding to 90 on the real part, and then the same thing with X prime and Y prime. So we're going to use a couple of examples to kind of get used to using the Mohr circle construct to find our normal and shear strains in a rotated direction, if we know them in some reference direction or vice versa. We tend to use the Mohr circle a little bit more with strain than we did with stress. It's much easier in a lot of cases to use the Mohr circle version of the strain transformations. You're using the same concepts. It's not a different concept, it's just an easier way generally of expressing the strain transformations. So we'll start with this example. We got a rubber sheet here. So it's got a Poisson's ratio of about 0.5 because elastomers have a Poisson's close to 1/2. They're going to behave like a fluid. And it's 50 millimeters long in the Y direction, and we're going to yank on it and induce some strain. So we're going to stretch it in the Y direction, and we're going to take the this reference dimension in the Y from 50 to 55 millimeters. We've marked a coordinate system of interest where we have a direction A. This would be like the X prime axis here, and B, which would be like the Y prime. And they're at a right angle, and we could define the angle beta between them, which starts out at 90 degrees, and we're interested what's the strain that we're going to see. The shear strain, so what reduction in that angle beta? So by looking at the angle beta as the angle between what's basically a rotated coordinate system, we can use our Mohr circle strain transformation to basically get the shear strain. It's going to be represented by a change in that angle beta. We know that our X prime direction starts out at 10 degrees from X, so and it's in the counterclockwise direction. So that gives us a clue of where to start. So we start by calculating our reference system normal strains. So strain in the Y, EYY, is going to be change in length divided by original length, which gives us 0.1. And EXX, we can use basically use the definition of Poisson's ratio. So we have negative Poisson's ratio times our axial strain. In this case, that's EYY that we just calculated right there. And we've said this is rubber, so V is 0.5. So our strain in the X direction is negative 0.05. So we can come over to our Mohr circle and say, okay, we're going to plot Y here, and as our, it's Y is a principal direction. There's no shear, there's no imposed applied shear strain in the Y direction. We're not basically like rotating it. We're not twisting it and stretching it in the y direction. So y is the principal direction, so we can plot it right there on the Mohr circle, and so is x. X is going to have a strain, only normal strain, compressive in this case due to the Poisson's effect, but no normal. So it's our second principal strain. It's compressive. And we know that we know where the center of our Mohr circle is because it's 1/2 of the distance between our two principal normal strains. So we've got our center, and so we know the radius. We can draw the Mohr circle now. Once we have the principal strains and the radius, we can construct the circle. So that gave us a circle. Now we also know that our x prime direction is rotated counterclockwise 10 degrees from our x direction. Well, our x direction is here. Counterclockwise is in this direction. So I'm going to go 2 times 10 degrees rotation on the Mohr circle, and that's going to locate the x prime direction on the Mohr circle. So x prime on the Mohr circle is here, x prime on the real part's up here. 2 theta is 20 degrees. So I can basically establish the shear and the normal strains by just simply taking cosine and sine of that 20 degrees and multiplying by the radius of the Mohr circle. Just use a right angle trig. So this distance is going to be r, my marker quit, r sine 20. So that is going to correspond to gamma over 2 for this rotated direction. So if I multiply that by 2, I would get the gamma xy, which is going to be how much that angle closes up. So I can either use basically, I'll use my Mohr circle construct to get r. So I'll just do 0.1 minus 0.5 divided by 2 to get my r, and work through, multiply by sine 20, so, and then multiply by 2 to go from my tensor shear to my engineering shear. So sine 20 times 0.075 times 2 ends up giving me my engineering shear in the xy, which is the same as the rotated coordinate system shear at my x prime direction. So that ends up being 2.94 degrees. So this new angle would be 90 degrees minus that. Okay, so that is steps that we had to go through. First, we had to establish our x and y direction on our real part. We had to understand how displacements related to strains. So we knew we displaced 5 millimeters in the y direction, so we got our strain in the y. We used the Poisson's ratio to get the resultant strain in the x. Then the next most important thing we recognized was that those were the principal directions. We had no applied shear in the x or y, so there was only tensile or compressive strain in those directions. So we knew that those were 2 points that were on the strain horizontal axis of a Mohr circle and that they were 180 degrees apart. So that basically, that and the relationship between those 2 points and the circle center gave us our circle center, gave us our circle radius, so we had our Mohr circle. Next most important point was to say, okay, where is the rotated x-axis on our Mohr circle? So for that we use the 10 degrees counterclockwise relationship between x and x prime direction, so that's our theta angle on the part. We found that on the Mohr circle using 2 theta on the Mohr circle equal theta on the part. We got our point. Then the next important concept we had to relate was shear, shear strain at x prime being corresponding to the closure of this angle. So basically we used the definition of shear strain and said, okay, shear applied at this x prime direction is literally equal to this angle closure. So we invoked, the fundamental definition of shear strain and then represented that as simply a y-axis, quote, a vertical axis. This is a vertical axis or a gamma over 2 axis coordinate on the Mohr circle. So it's a lot easier than trying to envision how much is this line going to come over and come up, or trying to calculate some displacement of those 2 coordinates. We just have to basically get the corresponding shear if that goes with our x prime. And you'll notice if we said, well, why couldn't we get that corresponding shear at y prime? It would give you the same shear, because if you look at where y prime is, it's 180 degrees. Again, counterclockwise from x prime, so y prime's over here, and this angle is the same as that angle, and the radius is the same. So basically it would be, it would be represented in the opposite direction, but it would give you the same magnitude. So we could look at the shear at x prime or y prime, and it would give you that that angle closure by definition of shear. Okay, let's do one more example that's a little bit simpler, but it also incorporates Hooke's law. So we're going to go with the simplest case, but it's the one from which a lot of material properties are drawn. So we're going to look at strain transformations and Hooke's law to relate our elastic constants, our Young's modulus, our Poisson's ratio, and our shear modulus. And we're going to use a homogeneous isotropic material like, steel that hasn't been cold rolled very much, or most thermoplastics that haven't been extruded. A lot of materials you work with are homogeneous and isotropic, and we're just going to apply uniaxial tensile stress as if we were doing a tensile test. So this is going to represent a lot of properties that you might look up in a handbook. They would be obtained this way. So we're going to establish a coordinate system, a reference coordinate system. So x is vertical, and here's our applied stress in the x direction. We're not applying any stress, in the y direction. We're applying stress in the y. We're not applying stress in the x. So notice we're not applying any shear. So we're applying stress in the y direction. That is, since we're not applying shear, there is no shear stress in the y direction or shear strain. So that is a principal direction, and likewise with x. So we effectively have 2 points on the Mohr circle and the center, just simply because we do have those are on our Mohr stress circle, because we have those 2 points. So let's start with our Mohr circle for stress. We have our y direction here represented by normal stress, so sigma 0 in the y direction. And then x is 90 degrees on the part, 180 degrees on the Mohr circle, and it's at 0 because we're not applying any stress. It's a free surface. So halfway between the two, we're going to have our circle center, and we've also established the radius, so 1/2 of sigma 0 is going to be our max shear. So we're going to, now we have max shear stress in terms of our applied normal stress, and so we have that to work back through our relationships relating these elastic constants. So now we flip over to our strain Mohr circle. Well, if x and y are principal directions, or reference x and y are principal directions for stress, they're also principal directions in this case anyway for strain. So here's strain in the y, and here's strain in the X. And we'll have our strain Mohr circle center somewhere, and its max will correspond to the radius tau max will correspond to just the difference between our first principal strain and our second principal strain divided by 2. So first minus second, which happens to be negative, so it'll be plus second divided by 2. So it's just the geometry of circle center to get radius. So this is again our gamma over 2, or our tensor strain. So this is EXX. XY, excuse me, shear, tensor shear strain. So that's gamma over 2 max. It's going to have this relationship. So now we have a great way to represent maximum shear strain in terms of our first principal normal strain in the direction we've loaded. We have Poisson's ratio, we have a constant, we've got our applied stress over here, and we have our max shear stress. So we wanted to relate these three constants together for this uniaxial tensile loading. So now we got to go back kind of to Hooke's law and start filling in some gaps. So we can relate shear strain in the normal direction to shear stress in the normal direction and elastic modulus. So this relationship, we can drop that in anywhere we see EYY. We can basically put a point over here. Our second principal strain is related to our first by Poisson's ratio, just like it was in our previous example. And if we have a relationship for EYY in terms of stress and Young's modulus, we can do the same thing for EXX, because EXX is just EYY times negative Poisson's, so we're going to drop that relationship, move an E over here. So that's, and that should have been over, and correct that. Then we can relate shear stress to shear modulus times shear strain. That's engineering shear strain. We can do some math magic and pull a 2 out, and then have our tensor shear strain here, which we can then relate to something on our Mohr circle, on our shear strain Mohr circle. Rearrange a little bit. Now we can just collect terms. So starting with our max shear strain up here, that was equal to this collection of terms. If we pull an EYY out, we can substitute in for EYY over our Young's modulus. In this case, EYY is our applied stress that we applied up here. And so we're left, out of here we got a 1 here, plus minus Poisson's divided by 2, so that's this part. So let's see, shear strain is going to be equal to, up here, shear stress divided by 2 times the modulus. And that, we can go a little bit further and say, okay, tau max is going to be equal to our applied uniaxial normal stress in the Y divided by 2, because we got that off of our stress Mohr circle. So now we have some expressions that basically have the applied stress 1/2 1 plus Poisson's ratio equals applied stress over 2 divided by 2g. So if we write all of this in terms of just the applied stress and the elastic constants, we end up with our applied stress over E, first term, times 1/2, coming down here, 1 plus Poisson's ratio. We have applied stress divided by 2, that's these first two terms, and then 1 over 2g. So we end up canceling everything that's common to both sides and rearrange, and we have actually verified our relationship between shear modulus and Young's modulus or tensile elastic modulus and Poisson's, just simply using uniaxial loading and two Mohr circles, Mohr stress circle and a Mohr strain circle. So that is it for derivation of strain transformations using geometry, chain rule, definition of strain and displacement relationships. We didn't go through every step rigorously, but we showed how they could be rearranged to give the cosine, sine, 2 theta terms that could be used to plot a Mohr circle. We reinforced how angles in the part, relationship between an x and an x prime, any kind of rotation angle on the part is represented by twice that angle on the Mohr circle. Picked key points of recognizing no applied shear stress or directions in which we know there's no shear stress, like a free surface where there's no shear applied, for instance, where we can identify those as principal shear-free directions on the horizontal axis of the Mohr circle, and then use those relationships to plot critical points, find max shear strain, find max normal strain, or shear and normal strain in any direction. And last but not least, we combined the Mohr stress circle and the Mohr strain circle to relate some elastic constants, and presumably you could use both of those together to relate state of stress and state of strain at any orientation in a part, because you may be limited by stress or strain in any given engineering design. So we'll have some more practice problems with the Mohr strain circle, especially with respect to measurements, when we do strain measurements on a given part using things like strain gauges.